Okay, now we are here. Okay. So this is a continuous one. Okay. This is a continuous. We are given a hint here. Okay. So ideally speaking, Nyquist sampling theorem can be never satisfied for the decaying exponential signals such as DFT above. Yes, that is correct. Okay. Because if we go this one, okay, so this is ut, okay, so that means only 0 to plus infinity is there, okay, so your signal will look like this, okay, so this will be 1, okay, so this is e to the power 5, e to the power 0.5t, okay. So you can see that we have to so this is the frequency, fundamental frequency 0.5. Okay, so there is no point to take the sampling frequency as half to sorry double of this frequency, because this is a monotonically decreasing signal. Okay, so if there is a monotonically increasing or monotonically decreasing function, and also maybe a discrete signal like DC signal like this, this Nyquist theorem is not not applied actually. Okay, this Nyquist sampling theorem cannot be applied. Okay, so it is better to get the samples as much as possible. Okay, then you can generate the signal there. Okay, I think when we have seen that when it is a sinusoidal case also, okay, sometime if we get this, if we consider this Nyquist sample theorem, it is not better. We have to get we have to get the samples as much as possible. Then we can reconstruct the signal appropriately. Okay. 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 So assuming that the magnitude of the continuous time Fourier transform is monotonically discrete with higher frequencies, and we neglect any frequency compact. Okay. So we are asked. The hint asked to assume the magnitude of the continuous time Fourier transform g omega. Okay. So we can calculate the g omega here actually. Okay. So if we calculate the g omega, okay, g omega, it will be 0 to infinity. So I think you can remember the Fourier transform for the continuous time signal. Okay. So if there is a continuous time signal xt, okay, and if we get the Fourier transform, this will be x omega. Okay. So x omega will be equal to minus infinity to plus infinity xt e to the power minus j omega t dt. Okay. So this is the definition. Okay. So clearly, okay, so maybe you couldn't remember that one. Okay. Okay, so we have xt signal, okay, and if we get the Fourier transform, we will have x omega. Okay, so this x omega we can evaluate through the integral minus infinity to plus infinity xt e to the power minus j omega t dt. Okay, so this is the Fourier transform definition. Okay, so if I apply this definition to here, okay, so easily we can, because this is a exponential terms. Okay, So we have e to, so here we have to 0 to infinity because our function is only from 0 to infinity. Okay, because this is multiplied by ut. Then we will have 0 to infinity. This will be cancelled. The minus side will be cancelled. Okay, so 0 to infinity e minus 0.5t e to the power minus j omega t dt. Okay, so if I calculate this, I will get, okay, I will get so my integration will be, so you can see that this is minus, I can get minus out, okay, and t also common, okay, so I can get minus 5t, so there will be 1 plus omega, okay, 1 plus omega. So if I write it like this, we have this way 0.5t, okay, 0.5t 1 plus omega, okay, divided by also 1 plus omega, no, 1 plus omega minus 0.5, okay, so this will be the integration, no? Okay, so you have to divide it by this constant minus 0.5 1 plus omega, correct? Okay, so this will be 0 to infinity. Okay, so this g omega will be, I have to apply these limits instead of this t. Okay, so if I apply infinity, okay, so you can see that at infinity this function is reaching to 0. Okay, this is going to be 0 at infinity. Okay, so if I apply infinity here, okay, if I apply infinity here, this will be 0. Okay, so it is 0 minus, okay, so if I apply 0 here, so this will be 1, and you will have this one 0.5 1 by omega. Okay, and this will be minus. Okay, so minus minus it will be plus. Okay, so this 0.5 if I get up, I will get 2 plus 1 by omega. And so this is the g omega. Okay, this is the g omega. So have I done any mistake here in my calculating? Okay, so this is the process. Okay, maybe please check if I have done a numerical mistake. So this will be plus 2 divided by 1 by omega, no, because this infinity is 0 minus minus, so here it is 1. Okay, correct. Yeah, maybe. Okay, so this one. Okay, so this is the g omega. G omega 2 divided by 1 by omega. Okay, so this will be the g omega. Okay, here the j is there, no? Okay, we have to consider that j also. Here j is there. I think this is my calculation is wrong. Okay, let me do it slowly. Let me do it slowly. Okay, so here e omega I can written as 0 to infinity. Okay, so so here so we can add them together. Okay, we can add them together. So I can get minus t only. I can get minus t because these are not common. Okay, I have done a mistake. Okay, minus t only. Okay, so that I will have 0.5 plus j omega. Correct. This is the thing I have. Okay, 0.5 plus j omega. So I get minus t. So I have 0.5 plus j omega. No? Okay. Okay, now if I do the integration, okay, it will be e to the power minus t 0.5 plus j omega, okay, divided by, so this is minus sign is there, minus 0.5 plus j omega, okay, and we have to apply the limits, okay. So after apply limit, so this will be 0, okay, so this will be 0 minus, so here when I apply the 0 instead of this t, it will be 1, so I will have 1 divided by 0.5 j omega, okay. So this is the thing I get, okay. Actually this should be a complex value, okay. That is why I double checked it. In previous side we got 1 by omega without this j, okay. So the j should be there, it should be a definitely it should be a complex value, okay. So here I can get gw as, so here minus minus I will get plus 0.5 plus j omega. I think this is correct, okay. You can check it, okay. So you can see that this is a complex number. You can make this as x plus iy, okay. If you multiply this minus 5 minus j omega, then you can do some mathematical manipulation and you can get this j omega in this x plus iy form, okay. So that is that, okay. So what is they asking? They asking that we have to get the magnitude of this j omega, okay. Magnitude of j omega, and is motorically decreasing with the higher frequency, and okay, so we will see the magnitude of this j omega, okay. So we will use MATLAB to check that, okay. Still I have no idea about this question, how we do, okay. So I am trying to get idea here, okay. So this is 0.5 plus j omega, no, okay. So I can okay, now I am in MATLAB, okay. So now I can set this omega that is from 0 to, so this omega is a continuous value, okay. This continuous value, so I get some very small point, okay, to look it as a continuous, okay. Let's take it up to 30 or something, okay. And if we write the g omega, it will be 1 divided by 0.5 plus j omega. J I write as 1i, okay, j omega, okay. So j omega, okay. So if I plot it, plot this g with respect to omega, okay. Now I have to plot the absolute value, okay. So I have to plot the absolute value because I have to plot the magnitude, no. Okay. So I have to plot the absolute value, okay. So if I plot this, let's see. Okay. think it may be okay. Okay, so for this multiplication also you can put the dot sign. Okay. Okay, you can see that it is monotonically decreasing. Okay, it is decreasing. Okay, that means when it go to the very high frequency, it will be decreasing. Okay, so this is the frequency. Okay, this is the frequency axis. This is omega. Okay, we have to plot uh, the magnitude. So this is the magnitude with respect to omega. Okay, so you can see that when the frequency is increasing, the magnitude is decreasing very quickly. Okay, so here it is true, no? Okay, this g omega is also monotonically decreasing. Okay, this g omega, this g omega is also monotonically decreasing with higher frequency, and any frequency component at which the magnitude falls below certain threshold value. Okay, so it is said that so we can see that this g omega is monotonically decreasing like this. Okay, it is decreasing, and after some frequency component, okay, let's say some value, okay, I don't know the value, omega naught or something. Okay, so after that value, okay, we can neglect the other values because those are very small. Okay, so here we are asked to set the threshold value neta, and neta is equal to 0.01 GW max. Okay, so what is the maximum value that get to here? It is 2, no? The maximum value is 2. You can check it here. Okay. So if you see this G, okay, actually you have to, we will take the absolute value here. Okay, here I get the absolute value here. Okay, so I no need to use this this absolute here. Okay, because here directly I calculate the absolute value, then we can see the values. Okay, so I will get the same result, no change. Okay, so we will be getting the same graph. Okay, so only thing is I put absolute here. Okay, so I can see the absolute value actually. That is why I put. Okay, so you can see that maximum value is 2 actually. This is the maximum value, G max. Okay, maximum value of this G max, that is 2. Okay, so they are asking, so this G max is 2 actually. Okay, so they are asking the threshold value is 0.012, no, 0.02. Okay, so after this value, they ask to neglect the frequencies. Okay, so we will see what are the values. Okay, so here we have some n value. Okay, after 0.2, 0.02, 0.02. So I will take here, it is still not 0.02. Okay, so I will get around 50 sample. Okay, we will see what happens, and you can see that we will have more frequencies. Okay, I think actually at 50 it is around 0.02, no, 0.02. Okay, still 0.02. I think we can get around 45. Okay, So I think if we get the frequency up to 45 something, okay, 45 something, that is okay. Okay, because you can see that it is around 0.02. Okay, 0.02 we have. Okay, so what is it's asking? Okay, so we can neglect those frequency component. Okay, so the high frequency component we can neglect. Okay, okay, that means so if we take this one, okay, if we take this one, okay, is it asking to neglect after this one? So here we have GT, okay, and it will be like this. Okay. Is it saying that we can neglect after 50? These frequencies we can neglect and we ask to take up to here 0 to 50. Okay, I'm not sure. Okay, but I think that is the thing they ask. Okay, up to 50. Okay, and you have to get the so you have to also sample this. Okay, also sample this with this frequency, no? Okay, so if I sample this, okay, so here we are not I can't understand how we can select the sampling frequency. Okay, how we can select the sampling frequency. Okay, I'm not sure this is for a sampling frequency or something. Okay, I'm not sure. Okay, but anyway, if we sample the signal, okay, so we will get this kind of signal. Okay, e to the power 0.5 n. Okay, 0.5 n. Okay, instead of t, we will get n. Okay, okay, actually we can't put n here directly. Okay, we can't put n directly here. Okay, because this n is related with the sampling frequency. Okay, so this will be the sampling period, and so this will be sampling period. Okay, and sampling frequency is 1 by t. Okay, so this will be the sampling frequency. Okay, so this will be the sampling frequency fs. Okay, so this n is always related with this sampling frequency. Okay, there should be a nominalized. We should have the nominalized frequency here. Okay, but I can't understand how it happened. Okay, so anyway, we can assume that Gn is equal to E 0.5 n. Okay, and this n is from 0 to 50. Okay, 0 to 50. I'm not sure. Okay, maybe they are asking this thing. Okay, I'm not sure, but if this is the case, we can evaluate the DFT here. No, okay. So we have 50 point. Okay, so we have 50 point. Okay, we have 50 point to calculate. Okay. Mm. So 50 point means it is very big number actually. Okay, so we have to find very big Fourier transform. Okay, that is not possible with the DFT actually. Okay, we have to do many addition and complex subtraction. Okay, But using the FFT algorithm, we can do this. Okay. Mm, so we have a sequence. Okay, in this logic, with this logic, we can get the sequence. Okay, like this: e to the power 0.5, 0, and e to the power 0.51, so on. We can get some sequence. Okay, so these are some real value, not a complex value. So we have j, we doesn't have j here, so we will have real values. So this will be our time sequence, and it can be converted to frequency domain using DFT. Okay, the problem is that if we have 50 component, we have to get very higher number of DFT. Okay. Okay. So, but okay. Uh, but it is very hard to do the calculation by hand. But we can use MATLAB to find this one actually. Okay. So you can see that. So we ask to estimate the frequency characteristic of the this one. Okay, maybe that is the thing he is asking. Okay, we plot this g omega. Okay, and we can see that when the frequency is going high, the magnitude of uh, Fourier transform signal, the the frequency domain signal is uh, rapidly decaying. Okay, so that may be the frequency characteristic. Okay, and they asked to plot the magnitude and phase spectra. Okay, actually for this one we can so we have already plot the magnitude and phase spectra, magnitude spectra. Okay, and phase spectra also you can plot very easily. Okay, instead of this ABS you have to put angle, no? Okay. Then you can plot the phase spectra for this signal. Okay, g omega, capital G omega, that is Fourier transform signal. Okay, but it is not the discrete Fourier transform, DFT. Okay, so anyway, DFT, to perform DFT, we should have a discrete time signal. Okay. Okay. Actually, for this one, you have to perform 64 DTF. Okay, DFT. Okay. Then you can get all the values without a problem. Okay. So you can calculate it using MATLAB actually. Okay. So so we can get k is equal to 0. Okay, 0 to 50. Okay, 0 to 50, 0 to 49. No, 0 to 49. Okay, because in -1 there should be in -1. Okay. No, I think if we get 64, that is good, because that is the point. Okay, we can 0 padded. Okay, so 64, that means up to 63. Okay, because I'm going to do the 64 DFT. Okay, 64 point DFT. Okay, because 64 is 2 to the power 6. No. Okay, so if we choose 2 to the power number, it will be easy to do the calculation. Okay, but in MATLAB it is not much problem. Okay, it will calculate anyway. We will get 63. Okay, and what is our signal xk? Xk I will take as e to the power, okay, to the power minus 0.5 minus 0.5 so you can see that. Okay, so this will be our signal Gn. Okay, that is e to the power 0.5 n. Okay, so this n from 0 to let's take up to 63. Okay, so this n is from 0 to 63. Okay, so we have xk. Okay, the definition is n equals 0 to n minus 1, that is 63. Okay, we have e to the power 0.5 n. Okay, and e to the power j 25 n k n. Okay, so this will also so this n will be 0. So if I write this again, okay, so here n is equal to 0 to 63. Okay, so we have e 0.5 0.5 n. Okay, and we have here e to the power j 2564. Okay, 2564 kn. Okay, kn. Okay, okay, now so this will be our xk. Okay, to find the xk, first we have to put the value for n from 0 to 64. Okay, okay, so we can calculate the xk like this. Okay, so n from, okay, actually here we have to use the for loop. Okay, otherwise we can't do this. Okay, for first loop, for loop is for n value. Okay, so n from 0 to 63. Okay, 63, we have to n from 0 to 63. No, the first for loop should be k. No? Okay, because first we have to calculate the n value, then we have to calculate the k values, no, corresponding k value. Okay, so that is the procedure. No, I think you can understand what I'm saying. Okay, if you have a problem, you can just ask. Okay, because you can see that here we have this one. Okay, here we have this one. Okay, to expand this, first we have to apply n is equal to 0 to 65. Okay, so we will have e to the power. So if I write this with the addition, okay, I will get this n as common. Okay, so I will have 0.5 plus j 2564k. Okay, so first I have to apply this n value. So n is 0 plus, so this is n is 0. Okay, and here n is 1 plus n is 2 up to n is 63. Okay, so we have to first apply n value, then we have to apply the k value when k is equal to 0, when k is equal to 1, so on we can calculate the xk value. Okay, so this should be, so here I am going to use the for loop for this one. So this will be my the second for loop, and this should be my first for loop. No, okay. So when we are writing the program, I think you can understand it. Okay, so I put k is equal to 0 to 63. Okay, 63. Okay. Inside this for loop, I again calculating another for loop. So n is equal to 64. Okay. Okay. So now I write the expression. Okay. Okay. 0.5 divided by n. Okay. Again, it should be, this should be multiplied by x. Okay. So here minus j is here. So 1i, 2j, 1i, 2pi, 2i divided by 64, no? 64, 64. Before that, kn also should be there. K n. Okay. This will be k capital. Correct. Okay. So we will have this one. So if you want, you can put this for safety. You can put more brackets for more safety. Okay. 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 And then end. Okay. Then, okay. So this will calculate the xk value. Okay. So I have to put another end. Okay. So let's check what are the values. Okay, so kx we have some values, no? Yeah. It should be xn. Okay. It should be xn. Let's calculate. So we put here 1 to 64. Okay. Looking the same thing. And the same thing. Okay, but anyway, it will not give much. Only one component is missing. No? Okay. You can see that we will have 64 complex number. Okay, actually here there should be 64 because 0th value is not here. Okay. If you want to get the 0, I think you can put like this also. If I put +1 here, it will be okay. So I will be relocating this, okay, as in the previous case, okay, because it can be changed. The length can be changed. So we are asked to fix it. Okay. So I can use this 0, 1 to 64. No? 64. So I think this will give us. Okay. So now you can see that in XK we have 64 value. Okay. So, okay, okay. So I think there's no any issue. Okay, so the same result we get. Let's check it again. Okay, so we have xk. Okay, so this is the xk value. Okay, so we have some. So these are the samples actually. We have 64 samples. Okay, so you can plot the magnitude and phase plot without any problem. Okay. So actually, before that, you have to have a k value. Okay, k, what is that? K array. Okay, so that is from 0 to 63. Okay, and you can plot. Okay, you can plot. This is the independent variable. Okay, and absolute value we have to get to that is for magnitude plots. So you have to get the absolute value of this xk. Okay, if I get the absolute value of this xk, okay, so I think this will give us the magnitude plot. Yeah, and that is missing. Okay, okay. So this kind of magnitude we plot we have. Okay, so you can see that. So this is so after k values is more than 10. Okay, the magnitude is reaching to 0. Actually this is not 0. Okay, because you can see some values are there. Okay, but it is very much near to 0. That is why we see it as in this x-axis itself, but it is not in x-axis because there are some value actually. Okay, so this is the magnitude plot. If you want to plot the phase, okay, you can put ANG. Okay. I don't know my logic is correct or not. Okay, uh, maybe my logic may be wrong. Okay, so if anyone have another idea, you can tell me, then I can correct. If my logic is wrong, I can correct it. Okay, so this is the things comes to my mind when I'm doing this question. Okay, so we plot. So we find the DFT actually. Okay, we find the DFT for 64 point DFT. We find using the MATLAB. Okay, so what we have done here actually. Okay, I don't know my logic is correct or not. Okay, so I get this discrete signal. Okay, so this in from 0 to 50. Okay, to perform the 64 DFT, I get 0 to 64. Okay, because 50 the DFT should be more if this n is 50 long. Okay, so this is the GN. Let's take this as GN. Okay, so this is the so if this GN is 50 long. Okay, this if the length is 50. Okay, we have to get uh, more DFT. Okay, more DFT point to reconstruct the signal. Okay, otherwise aliasing effect can be happen. Okay, so I take 64 point DFT. Okay, so I chose 64 point DFT. Okay, so I get 64 point here. Okay, 0 to 63. Okay, then I calculate the GK value. Okay, so GK is n is equal to 0 to 63. Okay, so Gn is 0.5 n e to the power j 25 divided by n kn. Okay, so this k also from 0 to 63. Okay, so I have evaluated this DFT using the MATLAB. Okay, because if I doing this by hand, it is very hard. Okay, so I use MATLAB. Okay, so we should have uh, G0, okay, capital G. I take capital G, G0, G1, so on up to G63. That is 64 elements. Okay, 64 sample. Okay, so in this XK, so we have this 64 sample. So these are the DFT point. Okay, these are the 64 sample we have. Okay, we have calculated. Okay, then we plot the phase plot. So we have 64 sample. Okay, so we have plot the phase plot. Okay, and magnitude plot. That means I get the GK, and also we can plot the phase also. Okay, to plot the phase, you have to put the angle here. Now I have plot the phase plot. Okay, so if you get the absolute value here, you can plot the uh, angle. Okay, so what is the conclusion you can get from this magnitude plot and phase plot? Okay, so after the n is greater than 10, this magnitude and phase are very much. So if I get the magnitude, so this will be the, so this will be the, uh, this will be the um, magnitude plot. Okay, sorry, and phase plot. Okay, so if I get the amplitude magnitude plot. Okay, so we will have this. Okay, so you can see that after 1020, this magnitude is very much near to 0. Okay, so this can be negligible actually. Okay, okay, so we can see it in this using this magnitude plots. Okay, so I think that is the thing. I don't know, my logic may be wrong. Okay, anyway, you can see my logic is wrong or correct. Okay, so if you have any idea, you can let me know. Okay, then I can, if my logic is incorrect, I can recorrect my mistake. Okay, okay, so we have used this hint. Okay, to get that decision. Okay, so still I also have doubt. Okay, my main doubt is about with the sampling frequency actually. Yeah? Okay. But here it is said that sampling frequency is not much. The Nyquist sampling theorem is not applicable here, or not satisfied here for this one. Okay, so maybe we can choose any sampling rate here. Okay, okay, so we will stop here.